Hello, everyone, and welcome back. I am Dr. Supradip Das, Assistant Professor at the Department of Design, IIT Guwahati, and this is the 21st lecture of the course Introduction to Toy Design. Today's lecture introduces ergonomics in toy design, but not in the usual sense of comfort alone. We begin by understanding what ergonomics actually means in this context. Instead of asking what children are capable of doing, we ask whether the toy fits how they interact in the present moment. Next, we will look at the two types of ergonomics, physical and cognitive, and see how each affects play differently. We will first explore physical ergonomics. Here, we will examine anthropometric data and understand how real body measurements guide toy dimensions. We will then look at reach and interaction zones, where children naturally interact with objects, and finally discuss weight and repetitive fatigue, or why a toy that works once may not work every time. After that, we will move into cognitive ergonomics. We will follow the full processing chain: sensation, attention, perception, memory, and reasoning, and see how information processing affects interaction. We will also discuss visual and perceptual ergonomics and how clarity influences understanding. Finally, we will examine instructions, feedback, and mental models and how children interpret cause and effect while playing. By the end of this lecture, you should be able to look at a toy and diagnose why children abandon it. You should be able to distinguish whether the issue is physical strain, mental overload, or emotional resistance. You should be able to justify dimension and force decisions using body measurement, logic, rather than guesswork. You should also be able to simplify interaction so children recognize what to do instead of remembering instructions. You should be able to design toys that remain comfortable over time rather than only usable ones. And most importantly, you should be able to design for sustained engagement, where children continue interacting voluntarily. In earlier modules, we focused on children development. We asked how children grow, how their motor skills change, how cognition evolves, and how emotional capacity develops over time. That lens is essential, but ergonomics asks a different question. Ergonomics is not about how children grow. It is about how design fits human capability in the present moment. Development tells us what children can do. Ergonomics tells us how design supports that doing. Development is about capacity. Ergonomics is about comfort, efficiency, and experience. A child may be able to grip a toy, but can they grip it comfortably for 10 minutes? or more. A child may be able to understand rules, but does the toy overload their working memory? That distinction alone prevents repetition of developmental theory. Ergonomics is not a repeat of milestones. It is about reducing mismatch between ability and interaction. Ergonomics in toy design is about designing for human fit. It is about preventing strain, physical strain and cognitive strain. It is about reducing mismatch between the user and the object. In toy design, this means asking different questions, not can a 5-year-old stack blocks, but is the block size comfortable for repeated stacking? Not can a child follow 3 rules, but does remembering those rules create unnecessary cognitive load? Ergonomics focuses on sustained engagement. Can a child remain comfortable and confident during interaction? When ergonomics is ignored, toys are abandoned quickly. Not because they are developmentally inappropriate, but because they are tiring, confusing, or frustrating. Ergonomics becomes visible when things go wrong, when a toy becomes physically tiring too quickly, we see fatigue. When precision demands exceed comfort, we see frustration. When frustration overload memory, we see confusion. When lights, sound, and movement overwhelm senses, we see overstimulation. When too many decisions are required at once, we see a cognitive overload. When failure is frequent or publicly visible, we see emotional resistance. These are not developmental failure. They are ergonomic failures. A toy can be aligned with age and still create hidden strain. Ergonomics allows us to detect those invisible stress points, and good toy design eliminates them before they appear. Ergonomics is not a single concept. It operates across 2 layers of interaction. Physical ergonomics deals with the body's relationship to the object. It asks whether the child can reach, hold, press, lift, and repeat actions comfortably over time. And cognitive ergonomics deals with the mind during interaction. It examines how much information the child must process, how many decisions are required, and whether the toy can be understood intuitively. Physical ergonomics deals with the interaction between the body and the object. In toy design, this includes body dimension, posture, reach zones, grip mechanics, weight, and repetitive strain. Children are not scaled-down adults. Their proportions are different. Their strength distribution is different. Their endurance is also different. A toy may be developmentally correct, but if it requires excessive wrist deviation, elevated shoulders, or a repetitive, forceful grip, it becomes ergonomically wrong. Physical ergonomics asks, can the child interact comfortably for sustained periods? Does the toy promote neutral posture? Does it reduce unnecessary strain? This is where anthropometry becomes essential. Anthropometry refers to the systemic measurement of the human body. For toy design, we are particularly interested in measurements such as standing height, sitting height, shoulder height, eye level, arm reach, hand breadth, and palm length. Data from Indian preschool children shows significant variation even within the same age group. There is no average child in practice. There is always a range. If we design only for the average, we exclude children at both extremes. This is why anthropometric data must guide toy dimensions. Grip size, toy weight, and control placement must all reflect real body measurement. Ergonomic design often follows the 5th and 95th percentile principle. This means that design controls must be reachable by the 5th percentile user and clearance must be ensured for the 95th percentile user. If you design only for the mean and average, you systematically exclude a significant portion of the users. Let me elaborate. For rich, grip size and access, design for the 5th percentile ensures the smallest children in your target age group can comfortably hold, press, reach out, or operate the toy. Example, button spacing, handle diameter, trigger force. If the smallest child can use it, most larger children can too. For clearance, openings, and space, design for the 95th percentile ensures the largest children in your target age group can fit comfortably. Example, armholes, sitting space, and head clearance in the ride-on toys. Simple rule to remember. First, design for the smallest when it comes to reach and control. Second, design for the largest when it comes to space and clearance. Good ergonomic toy design balances safety, comfort, and inclusivity across the full range of children in your target group. To achieve good ergonomics in toys, you must follow these 3 steps. First, clearly define the age group. Second, use anthropometric data for that age range. Third, often design for a range, not just one extreme. Anthropometric data gives us measurable reference points. It helps us understand body dimensions, reach, angles, and grip spans across populations. However, we cannot measure every individual child who will use our toy. That is neither practical nor scalable. Instead, as mentioned, designing for statistical ranges ensures that most users are physically accommodated. But anthropometric data is not the final answer. It is a starting point. Children vary in coordination, endurance, and posture habits. Two children of the same height may interact very differently. Therefore, after designing with anthropometric data, we must conduct real user testing. User testing helps us observe, is the grip truly comfortable? Does fatigue appear earlier than expected? Do children adjust posture in unintended ways? Data guides design. Observation confirms usability. Good ergonomics combines statistical grounding with lived interaction feedback. Hand ergonomics is one of the most critical aspects of toy design. Preschool children have shorter palm length, limited grip span, and developing fine motor control. Grip diameter must align with palm breadth data. If a toy handle is too wide, children compensate by overflexing fingers. If it is too narrow, they apply excessive force. Both create fatigue. Repetition amplifies this strain. 10 repetitions may feel fine. 50 repetitions may cause discomfort. So designers must consider duration, not just possibility. For children aged 4 to 5 years, hand breadth at thumb ranges from 5.1 centimeter for the 5th percentile and 6.8 centimeter for the 95th percentile. That means if your toy grip is 7 centimeter wide, you are excluding almost the entire lower half of the user. Now consider grip diameter. The mean grip diameter recorded was 3.3 centimeter with a 5th to 95th percentile range of 3.0 to 3.7 centimeter. If your toy handle exceeds 4 centimeter in diameter, you are likely forcing smaller children into overextension. Grip strength for 4 to 5-year-olds ranged from 2 kg for 5th percentile to 8 kg for 95th percentile. That is a massive range. So if a toy requires more than 2 kg of force to activate, you are immediately excluding at least 5% of the children, possibly more when fatigue is considered. Anthropometry allows us to make informed dimensional decisions. But remember, these are static measurements. Repetition and duration amplify strain. Ergonomics asks not just can they grip it, but also can they sustain it comfortably. Many toys are used seated on the floor or at low tables. Sitting height data shows variation in eye level and shoulder height among preschool children. If toy elements are positioned too high, children elevate shoulders, creating muscle strain. If too low, they bend forward excessively. Poor posture, sustained over time, causes fatigue and disengagement. Ergonomics aims for neutral joint positioning. The goal is not just access, but comfortable, sustained use. Let's look at a posture through actual ratios. For example, for children aged 3 to 5 years, sitting height is approximately 55% of the total stature. If average stature for 3 to 4-year-olds is about 96.7 centimeter, their sitting height would be roughly 53 centimeter. Similarly, eye height while sitting is about 94% of stature. That places seated eye level at approximately 43 to 44 centimeter from the ground. If your tabletop toy places critical visual elements at a 60 centimeter height, the child must elevate shoulders or extend the neck repeatedly. Now consider popliteal height, that is, the sitting knee height, which is approximately 23 to 24% of the stature. This determines appropriate seat height. When toy tables or surfaces are mismatched, children compensate by bending forward or elevating shoulders. Poor posture sustained for 10 to 15 minutes leads to early fatigue. Physical ergonomics prevents these invisible postural stresses. Children's muscle endurance differs significantly from adults. A toy that feels light to an adult may feel heavy after 5 minutes of play for a child. That is obvious. Upper limb strength develops gradually. Repetitive lifting, pressing, or squeezing can quickly cause fatigue. Fatigue leads to shorter engagement time. Shorter engagement reduces developmental benefit. Physical ergonomics therefore directly influences learning outcomes. The goal is to match toy weight and require force to child capability, not adult perception. Let's connect strength to body weight. In a Mumbai-based sample of 3.5 to 4-year-olds, mean weight ranged from 12.4 kg to 13.1 kg, with average height around 95 to 96 centimeter. This is a small body mass. Now connect that to grip strength data. For 4 to 5-year-olds, grip strength range from 2 kg to 8 kg. This means a child in the lower percentile may only exert 2 kg of maximum force. If your toy requires sustained pressing force near that limit, fatigue will occur within minutes. And fatigue changes interaction quality. Children may abandon the toy not because it is boring, but because it is physically demanding. Ergonomics translates strength data into realistic force thresholds for interaction design. Many toys technically function but are physically uncomfortable. Oversized components strain finger extension. Buttons requiring excessive force strain wrist flexors. Unbalanced toys require constant correction. Slippery materials increase grip effort. These issues do not show up in marketing materials, but they show up in shortened play duration. Children rarely articulate physical discomfort clearly. They simply abandon the toy. Physical ergonomics ensures that abandonment is not caused by strain. If physical ergonomics is about the body, cognitive ergonomics is about the mind in action. It is not about how intelligent a child is or about developmental milestones. It is about cognitive fit in the present moment. How much information is visible at once, how much decisions must be made, how quickly must the child respond. These are the kind of questions cognitive ergonomics makes one ask. Preschool children have limited working memory capacity. They cannot hold multiple rules simultaneously. If a toy presents too many instructions at once, the child experiences cognitive overload. Overload does not look like failure. It looks like disengagement. They may abandon the toy. They may misuse it. They may show frustration. Cognitive ergonomics asks, is this mentally manageable? Can the interaction be understood intuitively? Not only can they figure it out, but can they process it comfortably? Sensation is the first stage of interaction. Before understanding, the child must detect the stimulus. If visual elements are too small, they may not be seen clearly. If sound is too soft, it may not be noticed. If sound is too loud, it startles instead of informs. If textures are unclear, touch does not guide action. At this stage, the brain is not thinking yet. It is only receiving signals. If signals are too weak, they never reach awareness. Good design ensures signals are noticeable but comfortable. The child must detect before they can attend. Attention determines what the brain processes further. Selective attention allows the child to focus on one element. If multiple elements compete equally, confusion occurs. Sustained attention allows engagement over time. Rapid stimulus changes shorten play duration. Divided attention is limited in children. Toys requiring simultaneous monitoring overwhelm them. Shifting attention allows moving between steps. If interaction requires constant switching, fatigue appears. Design must guide attention intentionally. Primary interaction point should stand out clearly. Secondary decoration should not compete. Good toys reduce attentional conflict. Perception converts sensation into meaning. The child interprets what an element is for. For example, a protruding shape invites pressing, or a handle invites pulling. If appearance and function mismatch, the child must experiment repeatedly. Repeated trial increases cognitive effort. The goal is intuitive interpretation and consistent color coding and form recognition. This understanding should happen before instruction. After perception, information enters memory. Memory is not a single system. It operates in stages. The sensory register holds information for a very brief moment, just long enough for attention to select it. If a visual or sound cue disappears too quickly, the child never processes it fully. Next is short-term or working memory. This is where the child holds rules while acting. Working memory capacity is limited. Only a few elements can be managed at once. If a toy requires remembering multiple steps, the child forgets mid-interaction, not because they don't understand, but because they cannot hold the sequence. Finally, long-term memory forms patterns through repetition. When interaction is consistent, the child stops thinking about rules and begins playing fluently. Cognitive ergonomics therefore reduces recall, demands and increases visible cues and consistent patterns. The goal is recognition, not memorization. Reasoning is where the child tries to understand why something happened. During play, children continuously form small theories about the toy. They use different kinds of reasoning. Deduction happens when a known rule is applied. For example, if a button always lights the toy, it will light again. Induction happens when patterns are discovered through repetition. For example, every time the toy is tilted, the ball rolls. So, tilting controls movement. Abduction happens when the child guesses the most likely explanation. For example, something did not work because the button was pressed too softly. And introduction happens when the child invents a new rule to explore possibilities, such as what if they press two buttons together? Good toys support these reasoning processes, but inconsistent feedback breaks them. If the toy behaves differently each time without visible cause, the child cannot confirm or reject hypotheses. They begin rapid, repeated actions, not random behavior, but searching for logic. Cognitive ergonomics therefore ensures consistent cause-effect relationships, so reasoning leads to understanding rather than frustration. Now that we have looked at each stage individually, we can understand interaction as a processing system. The brain receives input, filters it, interprets it, decides, and acts. But this system has limited capacity. It cannot process unlimited information at once. When a toy presents too many elements simultaneously, the processing chain slows down. The child pauses, repeats actions, or shifts randomly, not because they are distracted, but because processing is overloaded. Each stage competes for mental resources. If perception requires effort, less capacity remains in the memory. If memory is overloaded, reasoning becomes unstable. So confusion often begins earlier than it appears. Information processing therefore asks designer to manage demand over time. Instead of presenting all possibilities at once, interaction should reveal complexity gradually. Good toys distribute cognitive effort. Poorly designed toys concentrate it. Cognitive ergonomics is therefore the management of processing load across interaction. Cognitive load refers to the total mental effort required to use a toy. Every rule, every button, and every color cues adds load. Consider a toy with 5 buttons, 3 sound modes, 2 light patterns, and multi-step activation. The child must remember which button does what, in what order, and what outcomes to expect. This is working memory stream. Young children typically manage only a few chunks of information at a time. If the toy demands sequential memory, press red, then blue, then green, the mental demand increases rapidly. Children perform much better when they can recognize what to do instead of recall what to remember. A visible shape cue is easier than remembering a rule. An icon is easier than remembering instructions. So when interaction depends on remembering sequences, the child is not learning the toy. They are managing memory. And when cognitive load exceeds processing capacity, confusion occurs. Confusion leads to emotional resistance. Designers must simplify decision pathways, reduce simultaneous inputs, reveal complexity gradually. Cognitive ergonomics replaces memorization with recognition and prevents invisible overload. Visual ergonomics is about perceptual clarity. If visual information is cluttered, the child must scan longer to interpret it. Scanning increases cognitive load. Small icons require closer viewing distance. Closer viewing alters posture. Poor contrast makes symbol recognition slower. If a button level blends into background color, the child must guess. Guessing increases cognitive effort. Interface parameters such as button size and feedback frequency directly influence mental effort. Now imagine a board with text instructions, background illustration, decorative graphics, and multiple color codes. Which element is primary? Which is decorative? If hierarchy is unclear, attention fragments. Young children are particularly sensitive to overstimulation. Too many flashing lights, too many simultaneous sounds, and too many competing cues. This is not engagement. It is perceptual overload. Good visual ergonomics guides attention intentionally. After visual clarity, perception determines interpretation. Before reasoning, children assign meaning to sensory cues. Perceptual ergonomics, therefore, assigns meaning to sensory cues. Color is not decoration. It is instruction and it highlights structure. Sound confirms outcome. When perception is clear, cognition becomes effortless. Color specifically guides behavior. Children respond to color emotionally before they respond cognitively. Warm colors like red, orange, and yellow increases alertness and activity. They attract attention quickly and are useful for interaction points or action areas. Cool colors such as blue and green have the opposite effect. They slow behavior and support longer engagement and concentration. Pastel shades reduce stimulation and are better suited for tasks requiring focus. Research shows children between 3 and 6 strongly prefer bright, high contrast colors and simple solid color areas. These colors are processed faster and attract attention more reliably. Complex color combination slow interpretation. The child must decide whether color indicates importance or decoration. However, problems occur when every element tries to attract attention at once. An environment filled entirely with bright colors does not improve engagement, it fragments it. The child keeps scanning instead of interacting. So color ergonomics is not about making toys colorful. It is about assessing behavioral roles through colors. Once color meaning is understood, we organize it using hierarchy. The 60-30-10 rule helps structure visual attention. 60% of the toy should be a dominant background color. This stabilizes perception and prevents constant scanning. 30% becomes a secondary color, supporting structure or grouping. The final 10% is the highlight color. This is where interaction happens: buttons, handles, and moving parts. Without hierarchy, every element competes equally for attention. Children then either press randomly or hesitate. With hierarchy, the toy silently communicates where to act. So color does not just decorate the toy, it becomes a navigation system. Now consider sounds. Sound in toys is both feedback and environmental exposure. A gentle click signals success. A harsh buzzer signals failure or interruption. If feedback sound is inconsistent, the child rechecks action. Rechecking increases cognitive effort. Predictable sound helps the brain close the action loop quickly. But continuous music or layered sounds interfere with interpretation. Instead of feedback, sound becomes background noise. Unlike color, sound cannot be ignored. It affects the body directly. Research shows continuous exposure above about 85 decibels risks hearing damage, and toys held close to the ear should stay approximately 65 to 70 decibels. However, many toys produce sounds above 110 decibels. Children also hold toys close to their ears, increasing effective loudness. Another important factor is frequency. Most toy sounds occur in the same range as human speech. So, loud toys don't just distract, they interfere with listening and communication. From an ergonomic perspective, sound should confirm action, not dominate the environment. Short, distinct feedback improves understanding. Continuous music and layered noise increases fatigue. Good sound design therefore protects hearing and supports comprehension simultaneously. Cognitive ergonomics also concerns how children understand cause and effect. If a button produces inconsistent outcomes, the child cannot form a reliable mental model. Mental models reduce effort. Uncertainty increases effort. Immediate feedback is essential when a child presses something. The response should be instant. Delayed feedback increases doubt, and doubt increases cognitive strain. Studies show that reducing response delay significantly improves operational fluency in interactive toys. Overly verbal instructions also increase load. Preschool children process spoken instructions differently from visual cues. If a toy requires listening and remembering simultaneously, working memory is consumed before play begins. Limited working memory means multi-step instructions dramatically increase failure probability. The child may understand the task but still fail during execution. Research shows that reducing voice response delay by 30% significantly improve operational fluency in smart toys. Children also seem to perform better when they recognize what to do rather than recall what they were told. A visible affordance is easier than remembered instruction. An intuitive toy communicates through form. Shape suggests function. Movement suggests possibility. Natural mapping reduces interpretation effort. Repetition and predictable patterns stabilize understanding. Children learn interaction through doing, not exploration. So, when children repeatedly experiment without clarity, they are not always exploring. They may be searching for understanding. So, cognitive ergonomics asks, is interaction predictable? Is feedback clear? Is understanding effortless? Mental friction is as real as physical strain. Today, we shifted our perspective from development to interaction. Development tells us what children are capable of doing. Ergonomics tells us whether the toy supports doing that comfortably. We saw that toys fail in invisible ways through fatigue, confusion, overstimulation, and emotional resistance. A child may abandon a toy not because it is boring, but because it is tiring, or not because it is difficult, but because it is mentally overwhelming. We learned that physical fit depends on real body measurements, not assumptions. We learned that cognitive fit depends on recognition rather than memory. And we learned that emotional fit determines whether children return voluntarily. So, ergonomics is not about making toys easier. It is about making interaction sustainable. A good toy is not one that works once, but one that remains playable over time. As designers, our responsibility is not only to enable action, but also to support comfort, understanding, and confidence together. As future designers always ask, does this toy truly fit the child it is meant for? Because when design fits the child, learning and imagination flourish. Design toys safely, design toys thoughtfully. Most importantly, design for smiles, giggles, and endless play. See you all in the next lecture. Until next time, have a creative and happy time.